All right, so we stopped after the examples yesterday. So picking up, we talked about independent yesterday, but independent does not equal disjoint if events are mutually exclusive they can't be independent. Use probabilities to complete a contingency table. Identify if the given data represents conditional or marginal probability So we'll look at an example of that. When stopping people for a suspected DUI, 78% of suspected drivers get a breath test. 36% a blood test. And then 22% get both. And so I'm going to draw a table and I'm going to fill in the stuff that was just given to you here, and then we'll have to fill in the rest. So we have breath test is going to be at the top. A blood test is going to be on the side. And then we're going to have that they received it, so yes or no, and then the totals for each thing. So we were told that 22% got both, so that would be a yes for both columns. So that was 0.22. %78 got a breath test, so that would be a yes in the total column for a breath test. So 0.78. And then the blood test, 36%, so that would go in the total yes for blood, which is 0.36. And we know the total that when everything is added up should be equal to 1, because probabilities always have to be 1. So we need to find these other 5 things, basically. So just a note though, the 78% and 36% are totals, or what we were calling early on in last semester, we were calling them marginal distributions. So I just want us to forget that term. And the 22% that have both is called a joint distribution. So basically, we're just figuring out, okay, these 2 things added together have to equal 0.36. So basically, what number needs to go in the no column for breath, yes for blood? 0.14. And then we do the same thing here. So we have 0.78 total. We had 0.22 that was yes for both. So now I need yes for breath, no for blood. And then I can find these other 2 totals, which will end up giving me the no and no. So I know the total going across the bottom has to be equal to 1. So that's going to be 0.22. And then the total going the other way to equal 1 has to be 0.64. So then my last box would be what? Yeah, 0.08. So ultimately, that's all that we had to do for that, was basically just asking to fill it out. But if we were going to do a Venn diagram to represent we have for blood, it would be the yes for blood, no for breath, so that would be the 0.14. For breath, that would be yes for breath, but no for blood, so that's the 0.56. And then the overlap in the middle, that was given to us to begin with, of 0.22, and then everything that was left over goes outside, meaning neither. All right, so this next thing is really important when you're looking at the problem. It's replacement or without replacement. So it's, are we gonna, basically, let's say you had a bag that had 10 different colored like tennis balls in it. And you had, some were red, some were blue, some were green. It's like when you take one out, are you taking it out and leaving it out, or are you gonna put it back in? Basically is what this next thing is. And the question should specify for you if it's being replaced or no replacement. So it'll say replacement or without replacement. So be aware of conditional probabilities. Due to non-replacement. Of possible outcomes. Think it through. And then another option of like kind of how you can represent it, we kind of did it very briefly right before Christmas, but was diagramming with like a tree diagram. So tree diagrams show sequences of events. It helps us reason through the situation. And calculate complicated probabilities. So while it is really useful, I don't tend to use them a whole lot because I get really irritated having to write everything out. But when they do get really crazy, I will use them. But that's not typically my go-to. So we'll look at an example of that here. And this example literally is an entire page, so just FYI. Okay, so basically, and it's going to be doing a big tree diagram, so basically we have 44% of students binge drink root beer, of course. 37% drink moderately. Good night. Somebody dying? Little kid just screamed. And 19% abstain. So then the next thing that comes with that, among binge drinkers, 17% have been in an alcohol-related accident. I guess I should say a root beer-related accident. And non-bingers, only 9% have been in an accident. Or alcohol-related accident, I guess. So I'm going to explain how we're going to draw the diagram, and then we'll actually go through and draw it. So the first branch separates, in this particular case, by type of drinker. So we're going to start out with 3 branches. All possible outcomes have to total to equal 1. So that means these percentages here should add up to equal 1, or 100%. Then, when we add in accidents, these numbers depend on drinking behavior. And obviously, like this one that says non-bingers have 9% have been in an alcohol-related accident. Like, obviously, if somebody's abstaining and not drinking alcohol at all, there's no way that they can be in an alcohol-related accident, like, that they've caused. Obviously, you know, whatever. We only care about them. So that one, the 9% is only going on the ones that drink moderately. All right, so then we're going to draw a big diagram. So we're going to have, let's see. Basically, it's going to look like this. And so I'm just going to go in order so that binge drinker, moderate drinker, or abstain. And then under that, we write the percentage, but we write it as a decimal for each. So binge was 44%, so it's 0.44. Moderate, 0.37. Abstain is 0.19. So that takes care of the first set. But then we have to add in the accidents based on the drinking behavior. So we then, off of each branch, have 2 possible ways that it can go. So basically, we can have an accident or none, like no accident. And then we would fill in the percentage values for those. So for a binge drinker, 17%. So that would be have been in an accident, so 0.17. The non-binge drinkers is 0.09. Obviously, if they don't drink, they can't be in an alcohol-related accident, so that would be 0. Now, each set of branches has to add up to equal 1, so we're basically doing 1 minus whatever this is. So this one would be 0.83 for none. Then for moderate, 0.91. And then for none, for abstain, would just be 1. Okay, we'll come back to that in just a second. So if we wanted to find the probability that they're a binge drinker intersected with that they were in an accident, we're using the formula, the probability that they're a binge drinker times the probability of an accident given that they're a binge drinker. And so the way that we have this laid out, actually everything is already there for us. So the probability that they're a binge drinker is 0.44. So 0.44. And then the probability that they get in an accident, given that they're a binge drinker, is just this other branch off of here where we have accident coming off of binge. So that would be times 0.17. Which ends up being 0.075. And so if we wanted to find the totals for all of them, that's basically what we're doing. We would just multiply all the way across and get the value for the probability that both of these things occur. So if we were going to do like binge and that there was no accident, all we're doing is multiplying 0.44 times 0.83. And I have all these multiplied out, so I'll show you what they are. But 0.365, then 0.033, 0.337, and then 0 and 0.19. Now, those numbers are not going to add up to 1. Obviously, they're not having something in common there. So that's why the diagram is nice. It's just really tedious to draw it out. So I really don't do it that often. I usually just find another method if I can. If we were going to just do the probability that someone got in an accident, that's just adding up all the percentages of accidents. Well, I should say, not these numbers. It's adding up the numbers that are written in green for accident. So it would be 0.075 plus 0.033 plus 0. Because we want the total, like, accident, not the accident for each individual thing. And that is 0.108. And this is, we just did this by adding all three joint probabilities. So basically what's written in green are the joint probabilities. And if we wanted then, just for the last one here, I think it's the last one, yeah. The probability that they binge given that they've been in an accident. So this one we can't just get off of just looking up here. We have to do a little bit of calculation. This would be the probability that they binge intersected with an accident divided by the probability that they've been in an accident. So binge and in an accident is the 0.075 over the probability they've been in an accident. That's what we just found, which is 0.108. And when you divide that, that equals 0.694. So that would be that probability there. Before we go to any other examples, though, I do have a question. How much do you know about a deck of playing cards?
I know that there's 52 cards, 13 for each set. It's pretty much it. Like, I don't know about the jokers or nothing.
Yeah, we don't count those. Just like a normal 52 card deck.
But yeah.
Okay, I'm just checking because that tends to be a problem. People tend to not know anything about deck of cards.